In the last video, we considered Legendre functions, which occurs in systems with spherical symmetry. And, we're able to see how to generate Legendre functions using Rodrich's formula, using recursion formula. And of course, we could actually, we also saw associated Legendre functions and things like that. So here we're looking at something still connected with legend functions called spherical harmonics. The common thing there is the idea of spherical coordinates. So that's why here we're looking at spherical coordinates again, though we saw that in the last video already. Then from there we look at angular momentum, we see spherical harmonics, orthogonality and completeness, associated legend polynomials, which we already also saw in the last video. Then we look at addition theorem, multipole expansion, multipole expansion, and applications of physics, as well as some Python examples. So the motivation for spherical harmonics is the first one we want to see. So spherical harmonics arise naturally whenever physical systems possess rotational symmetry. Okay, so they appear in quantum mechanics, electromagnetism, gravitation, acoustics, geophysics, atomic physics, and typical problems include hydrogen atom wave functions, electric potentials, gravitational fields, wave equations, and spherical harmonics are the spherical analog of Fourier series. So again, we saw spherical coordinates in the last video, talking about the fact that the relationship between Cartesian and spherical coordinates is as follows, that x is r sine theta cos phi, y is r sine theta sine phi, and z is r cos theta, where r is the radial distance, theta is the polar angle, and phi is the azimuthal angle. Okay, and then we see the just like before in the last video, also we saw the Laplacian in spherical coordinates. The Laplacian operator then becomes del squared, which is 1 over r squared d dr of r squared d whatever dr. So if like in the last video we had d squared v, so we just have v here plus 1 over r squared sine theta d d theta sine theta d d theta plus 1 over r squared sine squared theta d squared d phi squared. So the angular part of this operator leads directly to spherical harmonics. So the angular part leads to spherical harmonics. And how does that come about? We have angular momentum operators. Angular momentum is defined by L equals R multiplied by P. So the components are then this. You have L sub X, talking about angular momentum, that is minus I H bar into Y d dz minus Z dy. Then Ly is minus I H bar z dz minus x d dy. So this is, I believe this is some kind of vector um I think vector product, right? Talking about matrices now. And then you have LZ to be minus I H bar x d dy minus y d dx, depending on whatever you're looking at. Then we then have the total angle momentum to be L squared equals LX squared plus LY squared plus LZ squared. And then in spherical coordinates, that means L squared equal minus h bar squared into 1 over sine theta d d theta sine theta d theta plus 1 over sine squared theta d squared d phi squared. Then we have eigenvalue equations. So spherical harmonics then satisfy that L squared y sub Lm equals L into L plus 1 h bar squared YLM. And then we see LZ YLM to be M h bar YLM, where L takes value from 0 all the way, and so on, 0, 1, 2, and so on. And then we see M having been minus L plus 1 all the way down to L. So that's for the eigenvalue functions, still relating to all the whole angular momentum talk. Then we have the definition of spherical harmonics now, which is the essence for this video itself. So the definition of, as you can see already, I made mention of the fact that we have a lot of special functions talk coming up in mathematical physics. So here you're seeing harmonics, you're seeing things that you'd naturally just see in physics and all that. So the normalized spherical harmonics would then be y sub Lm of theta comma phi equals minus 1 raised power m square root of 2L plus 1 into L minus m factorial all over 4 pi all over L plus m factorial p sub lm, square root just covers this part, then the other part now, p sub lm cos theta e raised by im phi, where p sub lm are associated. So these are associated Legendre polynomials, which we saw in the last video. I think we're going to see it again here. Then we have L to be the angular momentum quantum number, and m is the magnetic quantum number. Okay. So then we have the lowest order harmonics. So it's usually good to find the lowest so that we can build on them to get other ones. So the lowest order harmonics, first of all, you have the angular momentum quantum number. When it is zero, you have y 0 0 equals 1 over square root of 4 pi. That's more like 2 root pi. So this represents spherical symmetry. And then you have, for L equals 1, you have y1 0, which is square root of 3 over 4 pi cos theta. So that means y1 plus or minus 1 is equal to minus or plus square root of 3 over 8 pi sine theta, e raised power plus or minus I phi, like that. And then we also talk about orthogonality, which we saw in the last video too. Spherical harmonics satisfy the orthogonality relation. The expression here is now different. Integral from 0 to 2 pi, integral from 0 to pi of y sub lm, y l prime m prime star sine theta d theta d phi equals delta ll prime delta mm prime. This property makes spherical harmonics an orthonormal basis on the sphere. In case you're wondering what orthonormal basis are, you may want to check uh, my playlist on, I think, abstract or most likely linear algebra, where we talk about things like orthonormal basis and all of that. Then we talk about completeness now. Any sufficiently smooth function on a sphere can be expanded as f of theta comma phi. This is the uh, uh, theta is the azimuthal angle, right? And I mean, phi is the azimuthal angle, and theta, we saw that in the beginning, that theta is actually the polar angle, yeah? Polar angle and azimuthal angle. Theta polar, phi azimuthal. So talking about completeness, then we have any sufficiently smooth function on a sphere can be expanded as f of theta comma phi. It's a function of the polar angle and the azimuthal angle, which is some summation from L equals 0 to infinity, summation from for M equals minus L to L, ALM, YLM of theta comma phi. Then the coefficient, this ALM now is integral of f of theta comma phi y sub lm star d omega, where the omega itself is sine theta d theta d phi, like that. So example, imagine that you want to expand f of theta equal cos theta. So since y1 of 0, like we saw before, is square root of 3 over 4 pi cos theta, then we obtain that cos theta itself now is actually, so it's more like make cos theta the subject. So you have square root of 4 pi over 3 multiplied by y1 of 0. That's what cos theta will be. So, and that means only one spherical harmonic contributes in this case. Then we have the Legendre polynomials. So, of course, we saw this before. So, Legendre polynomials can be generated. This is, of course, the Rodrigues formula we saw in the last video. So, that's a P sub L. So, the L we have here now is what we called N there. So, it's still the same thing, except that instead of N, we have L, this special L now. So, we have P sub L of x equals 1 over 2L L factorial dl dxl of x squared minus 1 raised power L. That's basically the Rodrigues formula for generating Legendre polynomials. Example now, for P naught of x, that means when L is 0 now, so P0 of x now, that'll be 1 over 2 raised power 0, that's 1. 0 factorial is also 1, so this whole thing is 1. So d0 dx0 means no derivative, and this is also 0. So anything raised power 0 is 1, basically. And then when L is 1, so you have P1 of x, that's 1 over 2 raised power 1, that's 2. 1 factorial is also is 1. So you have 1 over 2 here. Then d1, dx1, that's differentiate this once because the power here is 1. So it means just differentiate x squared minus 1, which is 2x. So 1 over 2 times 2x just gives you this x. And then on the other hand now, when L is 2, you have 1 over 2 factorial, 2 factorial. 1 over 2 raised power 2, 2 factorial. That's 1 over 2 raised power 2 is 4, 2 factorial, 2 factorial is 2. That's 1 over 8. Then you differentiate. So this is now x squared minus 1 power 2. Maybe I want to write that, right? So we want to get P2 of x so we have this that P we have P L of x to be 1 over 2 power L. L, okay, that's special L now. So L factorial d L dx L of x squared minus 1 uh, raised power L. So now, if that special L is now 2, so it means we have P2 of x equals 1 over 2 raised by 2, 2 factorial, then d squared dx squared into x squared minus 1 raised by 2. So we can then tidy this up. So we have P2, okay, P2, I thought I changed it, P2 of x equals 1 over 2 raised by 2 is 4. 2 factorial is 2. So we have that. Then d squared dx squared. So we can expand this. When we expand it, that's like x squared. X squared squared, that's x raised by 4 minus 2 times x squared times minus 1, that's minus 2x squared. Minus 1 times minus 1, that's plus 1. So we then have P2 of x equals 1 over 8. Then d squared squared, that means differentiate the first term, that's d dx of differentiate first term, that's 4x cubed, 4x cubed minus 4x plus 1. 1 is gone, that's constant. Then that means P2 of x now is going to be 1 over 8 d dx into differentiate this again. That'll be, oh, okay. When we differentiate again, this will be gone. So that'll be 12x squared minus 4. Now, P2 of x can then be said to be 1 over 8 times 4 is common into 3x squared minus 1. 4 here is 1, 4 here is 2. So P2 of x is equal to 1 over 2 into 3x squared minus 1. And that's exactly what we have for that. So with that in place, we have that 1 over 2 into 3x squared minus 1. Then we have the associated Legendre polynomials, Legendre function, which you saw in the last video also. Associated Legendre functions are defined by PLM of x equals 1 minus x squared m over 2 dm dxm PL of x. These functions determine the angular structure of spherical harmonics. If I did an example on this in the last video, so you want to check it out, that's the video on Legendre functions. So we talk about ladder operators. Define the ladder operators L plus or minus to be Lx plus or minus ILY. Their action on spherical harmonics is that you have L plus or minus L sub plus or minus YLM to be H cap, H bar, square root of L into L plus or minus M into M into M plus or minus 1. Then multiply by y sub L M raised by plus or minus 1. They raise or lower the magnetic quantum number M. That's what ladder operators do. They raise or lower the magnetic quantum number. So it's more like you're climbing a ladder, you're descending down a ladder. You're coming down from a ladder, you're descending on a ladder, right? So the addition theorem then states that we have P sub L of cos gamma to be equal to 4 pi over 2L plus 1, summation from M equals minus L to L of Y L M theta prime, phi prime, Y L M of theta, comma phi star like that, where gamma is the angle between two vectors. This theorem is fundamentally multipole expansions. So we have a special case where when the 2 points coincide, and that's where we have a summation from M equals minus L to L of YLM, or absolute value of YLM all squared, which is 2L plus 1 all over 4 pi. Okay, we have the two coinciding like that. So we have 2L plus 1 all over 4 pi that way. So that's you transferring this to the other side because you have a coinciding of the two like that. Um, So we then have multipole expansion. So for the multipole expansion and the electrostatic potential then is V of R equals 1 over 4 pi epsilon naught integral P of R prime all over absolute value of R minus R prime the 3R prime. Then the key expansion then is 1 over absolute value of R minus R prime because summation from L equals 0 to infinity of R L less than, then R greater than L plus 1, PL cos gamma. Using spherical harmonics, now you then have this, that 1 over absolute value of R minus R prime is 4 pi summation LM 1 over 2L plus 1, R L less than, R greater L plus 1, then gamma LM of omega YLM omega prime star, like that. Then we have the physical meaning of multipoles now. So first of all, we have we're talking about multipoles, right? So we have the monopole, which is V approximately 1 over R, which represent total charge. We have the dipole, which is V approximately 1 over R squared, which represents separated positive and negative charges. Then we have quadrupole. So the quadrupole is V, which is closely related to 1 over R cube, which represents more complicated angular distributions. Then you have dipole potential example. So the electric dipole potential is V of R comma theta, which is P cos theta over 4 pi epsilon naught R squared. Now using cos theta, which is square root of 4 pi over 3, square root of 4 pi over 3 multiplied by y1 of 0, which we saw the other time, we obtain that V is equal to P over 4 pi epsilon naught R squared, square root of cos theta now. So just like you have P over all of this multiplied by this cos theta, and then you have this. Thus, the dipole field corresponds to L equals 1 in that case. Then we talk about the hydrogen atom. The hydrogen atom wave function separates as psi of r or r comma theta comma phi, which is r sub n l of r, which is multiplied by y sub l m theta comma phi. The radial part is determined by the Schrodinger equation. The angular dependence is completely determined by spherical harmonics, like that. And then we have atomic orbitals. So the orbital types correspond to angular momentum quantum number L. So you have S. So this, I mean, we are going chemistry seriously here. So you have the orbital S and the quantum momentum quantum number S. The value of L is 0 for P. You have 1 for D. You have 2 for F. You have 3. The orbital shapes arise from spherical harmonics. You know, so it's more like we're already X-raying inside an atom. So we then have Laplace equation in this case. Laplace equation is del squared of V, which is 0. And then the general solution in spherical coordinates is V of R, comma, theta, comma, phi, which is summation over Lm of ALM R raised by L plus B sub Lm R raised by minus L plus 1 multiplied by Y sub L M, like that. Then we have gravitational physics. So planetary gravitational fields are expanded using spherical harmonics. So we have phi of r comma theta comma psi phi, which is equal to minus gm over r into 1 plus summation over lm r over r raised by l c sub lm y sub lm. So applications include satellite motion, earth geodesy, planetary science, and all of that. So then we have the Helmholtz equation. So the Helmholtz equation is del squared psi plus k squared psi equals 0, and its solution takes the form psi of r comma theta comma phi, which is equal to summation over lm of r sub l of r y sub l of m theta comma phi. So spherical harmonics describe the angular dependence in that regard. Then you have the group theory connection. Spherical harmonics form irreducible representations of the rotation group S03, and then for a given L, the number of states is 2L plus 1. This explains angular momentum degeneracy in quantum mechanics. Well, this is beginning to refer to abstract algebra. So in case you want to learn more about abstract algebra, you can check out the playlist on abstract algebra. Then we have the Clebsch-Gordon expansion. So we have products of spherical harmonics which can be expanded as YL1 M1 YL2 M2, which is summation over Lm of C sub L1 M1 L2 M2 super Lm multiplied by Y sub L super M. So the coefficients are Clebsch-Gordon coefficients. This govern angular momentum addition in quantum mechanics. So here we can have a kind of Python example, plotting spherical harmonics. So, you have the whole code going. Okay, yeah. You have the whole code going that way. So we need numpy, we need matplotlib dot pyplot. We need scipy. Okay, we need scipy where we import sph underscore ham, and then we have theta NP lin space. So for theta is from 0 to pi, just like it was defined before, and phi is from 0 to 2 pi. Either in this video or in the previous video, we talked about the range for theta and phi. So theta and phi, take the mesh grid for theta and phi. L is 3, M is 2. You can vary those values. Then you have your Y now, which is spherical harmonics, taking M and L, phi and theta as parameters. And then we have R, which is the absolute value of Y. Then you have x defined the way it should be. So that's r sine theta cos phi. Y is r sine theta sine phi. Then z is r cos theta. Then plot the figure, and that's we have here already. So this is how that looks like. So this is how this looks like. You can see how spherical it looks. So because we're dealing with spherical harmonics, then you can do an orthogonality check here as usual. So of course, it's always give 0, especially if uh these values are different. So if they are the same, let's see what happens. They are both 0. So we get some kind of, okay, it's still 0 here. So yeah, so we get that. So in all, we see in summary that we have some certain key results. Spherical harmonics satisfy L squared YLM equals L into L plus 1 H bar squared multiplied by YLM, and LZ YLM is M H bar YLM. So they form an orthonormal basis on the sphere, representations of rotational symmetry. They form representations of rotational symmetry, and they also form the angular part of it, many physical solutions. And you have applications including quantum mechanics, electromagnetism, gravitation, wave physics, atomic structure, and geophysics. So you then have a practice problems. So the first question says, show explicitly that y11 of theta comma phi is minus square root of 3 over 8 by sine theta e raised by I theta is an eigenfunction of LZ. So you have 2 here. Verify directly that all of this satisfy the eigenvalue equation of L squared. Complete the normalization constant of P21 cos theta e raised by I phi to construct the normalized harmonic Y21 and evaluate the integral as you see here. So here you see that they coincide. Okay, yeah, and verify normalization. Then that's you then have 5 to, I think we can show 5 to 9 here. So show that YL minus M is minus 1M YLM star for arbitrary L and M. Derive the explicit form of Y22 theta comma phi started from the associated Legendre polynomial. Determine the number of nodal lines for this. Prove that the spherical harmonics with different values of L are orthogonal. Okay, I think we saw things like this before. So when the values are different, it's orthogonal, that their integral between minus 1 and 1 is goes to 0. From minus 1 to 1 goes to 0. But if they are the same, you get some other values. Then we can then have 9 to say 13. Compute the commutator Lx, Ly, and verify the angular momentum algebra. Show that the ladder operator satisfies L plus YLL equals 0 for every L. Expand the function in terms of spherical harmonics. Expand this in terms of Legendre polynomials. Then derive the recurrence relation. Yeah, we use this recurrence relation a lot in the last video for Legendre polynomials. And using the addition theorem, evaluate P1 cos gamma in terms of spherical harmonics. So now we see the rest up to 20. Show that the monopole term of the multipole expansion reproduces Coulomb's law. Then derive the quadrupole contribution to the electrostatic potential for a localized charge distribution. Show that the degeneracy of angular momentum states with quantum number L is 2L plus 1 using properties of spherical harmonics. Solve the angular part of Laplace by equation by separation of variables and derive the spherical harmonic equation. Then compute the equation, the expectation value L squared for a particle in the state y3 minus 1. And lastly, write a Python program that plots the real and imaginary parts of y43 theta comma phi on the surface of a sphere. Okay, so let's go ahead and deal with, we'll be looking at problems 11 and 18 here. Problem 11 here says, expand the function f of theta comma phi equals sine theta cos theta in terms of spherical harmonics. That's problem 11. And for problem 18, we have to solve the angular part of Laplace's equation by separation of variables and derive the spherical harmonic equation. That's going to look like a big one, but let's see. Let's take it on. We've been doing that, so let's go. So I start with problem 11, which says to expand expand the function expand the function f of theta comma phi equals sine theta cos phi in terms of spherical harmonics, in terms of spherical harmonics. So we go for step one. Step one. Okay, well, let me forget about these steps. So the first thing, we want to recall the relevant spherical harmonics, right? So we see that the spherical harmonics, the spherical harmonics, the spherical harmonics for L equals 1 and M equals plus or minus 1, okay, are Y1, Y11 equals minus square root of 3 over 8 pi sine theta e raised by I theta. Okay, so we have something about sine theta and cos, right? Then that, right? And y1 minus 1 is square root of 3 over 8 pi sine theta sine theta e raised by minus I phi. This is not theta here, this should be phi. Okay. So since we have all this, right, the next thing is we want to express sine theta cos theta using exponentials. So now using cos phi, which is e raised by I phi plus e raised by minus I phi all over 2. So we obtain that sine theta cos phi can be expressed as 1 over 2 sine theta into e raised by I phi plus e raised by minus I phi. That's sine theta cos phi. So the next thing we want to do is to substitute the harmonics. So, we already have this, right? So if we have sine theta into this, we can, this is just a matter of rearrangement. So half comes out, the half we have is out here, then this sine theta is here, and then what we have left here is this e raised by I phi plus e raised by minus I phi. So it's just about rearranging, basically. Nothing special has been done so far. Then we go on to have the third step, right? So the harmonic definitions, from the harmonic definitions, then we have that sine theta e raised power I phi is equal to minus square root of 8 pi all over 3 yi1. Well, that's happening because from here now, so if we need just uh sine theta e raised by I phi, this goes over here and we have square root of 8 pi over 3. So we have it turning over. That's square root of 8 pi over 3 multiplying y11. That's why exactly we have this. So that's done. And then we also know that sine theta e raised by minus I phi will also be square root of 8 pi over 3 multiplied by yi minus 1. This is coming from this other side here, that, if you isolate this, now this goes and multiplies there, and then, it turns over to be square root of 8 pi over 3. Okay, like this. So, and once all of that is done, we can then say, therefore, sine theta cos phi equals 1 over 2 square root of 8 pi over 3, you know. Um, okay, that's like multiplying everything together. So we have 1 over 2 square root of 8 pi over 3 into yi minus 1 minus yi1. Okay, so yi minus 1 minus yi1. So it's more like putting both together. So if we put both together, we have something's canceling out, So uh yeah, because it's more like adding both together, right? So if you add both together so that this is this minus this. So adding both together, it's like we have sine theta. Okay, let me use another color. So you have sine theta e raised power minus I phi plus sine theta e raised power I phi, you know, equals, so add these two now. That's square root of 8 pi over 3, you know. So this is positive, then this is negative. So that's yi minus yi 1 up there. But see what's happening here. So this is sine theta into e raised power I phi, you know, plus e raised power I theta. So this is I phi, this is I phi equals all of that. But when it is all tidied up, so you can see this becoming this cos phi you have here now. Because cos phi can be expressed, um, so this is, yeah, one is minus, one is plus. Normally this should be, each of this is cos phi plus I sine phi rather. Then the other one is cos phi minus I sine phi. So this cancels this. So we just have, so we have 2 cos phi plus cos phi, that's 2 sine cos phi. So it is that 2 that comes here to divide both sides now. So that's where all of that is coming from. So everything here is coming from here. So this whole thing now is 2, because everything here is 2 cos phi, then sine theta that was there before. So that's what this side is becoming. And that's why this 2 goes to divide this side. And that's why we have all this expression. So you want to try all of that out as much as possible. But everything is logical for sure. So we have this. So with this in place now, we can move on. We have sine theta cos phi. Sine theta cos phi is all of that. And hence, we can say that exactly are we looking for? We're looking for to expand sine theta cos phi, which we have got already. So hence, sine theta cos phi is equal to is equal to okay, well, if you take the square inside, right, that's square root of, okay, before I say hence, right, I have, if you take this inside, that'll be 1 over 2 squared, times 8 pi all over 3. If you take this inside, right, so that'll be yi minus 1 minus yi 1, like that. So this will be square root of 1 over 4 times 8 pi over 3 into yi minus 1 minus yi 1. So that this is now 4 here is 2, 4 here is 1, 4 here is 2. So that'll be square root of 2 pi over 3 into yi minus 1 minus yi 1. So we can conclude then that hence we can say that sine theta cos phi is equal to square root of 2 pi over 3 into yi minus 1 minus yi 1. So that's what we need there. Okay, so we move on to another one, problem 18 now. Problem 18, which looks a bit tasking, or is it taxing now? So the question says to solve the angular, solve the angular part of Laplace's equation, Laplace's equation by separation, of by separation of variables, and derive the spherical harmonic equation. Okay, so we go. First of all, we know that Laplace's equation So solution of Laplace's equation is del squared V equals 0. We know that. And then we know that in spherical coordinates, in spherical coordinates, we know that we have del squared to be equal to 1 over r squared d dr into r squared d dr plus 1 over r squared sine theta d d theta into sine theta d d theta plus 1 over r squared sine squared theta d squared d phi squared. We have all of this in spherical coordinates. So if we then assume separation of variables, so if we assume separation of variables such that we then have v as a function of r theta phi, which is big R of small r, big theta, uh, how do I put this now? Okay, let me just do it. Big theta of small theta, then big phi of small phi, substituting, substituting, substituting into substituting into Laplace's equation. So substitute into the Laplace's equation. Okay. So after after dividing, after dividing by r, big theta, and big phi, okay, we've obtained this 1 over big R, 1 over small r squared, 1 over d small r squared, dr, dr, plus 1 over big theta, 1 over r squared sine theta, that's small r squared sine theta, d theta into 1 over r, 1 over dr, r squared dr, yeah. 1 over theta, 1 over r squared sine theta, d theta into sine theta, d big theta, d small theta, plus 1 over phi, plus 1 over big phi. This is a lot. Plus 1 over big phi, 1 over r squared sine squared theta. Okay, 1 over r squared sine squared theta, d squared big phi, d small phi squared. All of this is equal to 0. So after that's the separation of variables part now. So after dividing, that's what we get. So the next thing is we multiply by small r squared, because of this small r squared. So it can go out of this place. So if you multiply by small r squared now, so we have 1 r, 1 big R, then 1 big R. Okay, this is D here. So this is DDR. So 1 big R. So this is now DDR. That's DDR because R squared takes this out, takes the small r out. So into R squared dr, d small r, plus, again, R squared is gone from here. So we have 1 over big theta big theta, you know, um, sine theta d theta into sine theta d big theta all over d small theta plus 1 over big phi sine squared. Yeah, 1 over big phi. Okay, r squared is gone, right? Are we multiplied? So what big phi sine squared theta d squared big phi all over d small phi squared equals 0. Multiplying through by r squared. So that has taken care of all of these ones now. Okay, that's what that has done there. So here you don't see any of this r squared under anywhere. So we have that. Then we go to step 3 now. So step 3, we separate the phi equation. So we say the phi the phi dependence satisfies the phi dependence. So where do we have the phi thing now? So that's this guy. The phi dependence would satisfy that whole expression. So just extracting the phi part out, right? So the phi dependence satisfies that 1 over phi, 1 over big phi, 1 over big phi, d squared big phi, d small phi squared is equal to minus m squared, like some kind of constant. Thus, that means, just the normal thing we do for separation of variables, we begin to now form different equations with each of those. So we have d squared big phi all over d small phi squared. This is minus m squared, right? Um, so, if you multiply through by phi squared, you have that. So minus m squared big phi. So if you can bring it over, and that's m squared plus m squared big phi, and all of this is equal to 0. So, and this is a differential equation that can easily be solved, right? Um, you know, so whose solutions, whose solutions are big phi of small phi, and that is equal to e raised power I m phi. So e raised power I m small phi, you know, uh, where where we then have m to be equal to 0, plus or minus 1, plus or minus 2, and so on and so forth. So that's settled for the phi, for the big phi, for the phi part, right? Then we also have this. We want to derive the polar equation. So substituting, substituting the separation constant, the separation constant gives 1 over sine theta. Okay, that's too much. So that's 1 over sine theta d theta. The polar part is the theta part. So that's sine theta d big theta all over d theta minus m squared all over. That's like equating the theta part to m squared also. So that's m squared over sine squared theta big theta, and that is equal to minus lambda big theta again. Minus lambda big theta. So, or that becomes 1 over sine theta d theta sine theta d big theta all over d theta plus lambda minus m squared all over sine squared theta big theta here equals 0. Okay, tidying all of that up. So we can then convert variables, right? So we then have, we say let x be cos theta. Let x be cos theta. Then the equation, the equation becomes d dx into 1 minus x squared d big phi, d big theta dx plus lambda minus m squared all over 1 minus x squared multiplied by big theta. All of that is 0. So, and then this is the associated, this is the associated Legendre equation, which we've dealt with a couple of times. This is the associated Legendre equation. Okay. So with that in place now, this is something we're familiar with, so we can deal with that. So we can then do the quantization condition. So we know that finite solutions exist only if lambda is equal to special L into L plus 1, that L into L plus 1, where that L now is equal to 0, 1, 2, and so on and so forth. And the absolute value of M is less than or equal to L. So we know that the solutions are associated, the solutions are associated Legendre functions. So the solutions are associated Legendre functions. That's big theta of small theta is equal to P Lm cos theta, like this. And then we can construct the spherical harmonics. So combining the theta and phi parts. So we construct the spherical harmonics where we have y sub Lm. So this is L. So y sub Lm into theta into phi equals n Lm p L PLM PLM cos theta e raised power Im phi, where n Lm equals minus 1 raised power m square root of 2L plus 1 into L minus m factorial all over, okay, so to be more careful with this. So this is 2 special L plus 1 over 4 pi on one hand. On the other hand, we have L minus m factorial all over L plus m factorial, like that. So final result now, we see that the angular solutions, the angular solutions of Laplace's equation, are the spherical harmonics, are the spherical harmonics, which are y sub Lm theta phi minus 1 raised power m square root of 2L plus 1 all over 4 pi, then L minus m factorial all over L plus m factorial, then uh p then p Lm cos theta e raised power Im phi. So these functions, these functions form a complete, form a complete orthonormal, orthonormal basis of the sphere. Wow, that's a stretch. That's a stretch. But thankfully, we have come to the end of that. And that means we've come to the end of this particular video on spherical harmonics. So I've solved questions 11 and 18 out of this 20. So you want to try your hands on the rest. So here you have problems 1 to 4, 5 to 5 to 10, 5 to 10 here, then 11 to some maybe 16, so to speak, and then finally you have the rest. So try your hands on them and let's see how helpful let's see how well you can handle them. Let me know how helpful this is for your interest. Something else you'd like me to try out, feel very free to let me know. If you have not subscribed to this channel, why not? Why not go ahead right now? Subscribe to the channel and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join, which gives you special privileges. Gives special privileges. Um, so you'll find them out as you click on join. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.